Mute.
Okay. Fine. Yeah, and then if you share your screen.
Nope. It's wonderful stuff, technology.
Things difficult.
No, it's under. Well, been security or something. Where am I?
Did it just not make you co-host? Yeah, just make it co-host. Okay, you're now co-host, so you should be able to.
Right. Yeah. What is it? How do I get it to? There we are.
Yeah, still on this end.
Okay, and the camera is
Oh,
what?
yeah, camera, we don't use this. I can plug it into a laptop. It's a USB-A port.
There's one.
Yeah. And then. Yeah, it's a bit makeshift, but it normally works. And sometimes we clip it here, but the angle isn't great if we do that. The other thing I could do is I can.
You decide. I mean,
Okay.
It's your setup.
Well, I'll see what. If you can turn your camera on so we can see what the see what it looks like.
Sorry, what do I need to do? Oh, wait a minute.
Should be the video.
Yeah, I know it's got. I've got to. Oh, come on, silly thing. Can't find the.
If you hold on the green bar, it might there you go. And if you press start video, should.
Yeah. That's it.
Okay, and then you want to switch the input. If you go back on the on the bar, and if you go over to stop video and click on the arrow, yeah, pro webcam, it should be R1. Yeah, there you go.
Okay. It's not paying attention to it is. Okay.
Move it back a little bit. It's good to me, I think. That's.
Whoops. Okay, well, it's telling me it needs to be restarted to properly deal with your thing. I'm going to ignore it.
Yeah. Okay. It should be fine, I think.
I'm glad we were not late.
Yeah. Yeah, this is why we get here for 7 o'clock.
Yeah.
Just so we can sort out any issues. At least we don't have the issue that we had last year where the whole lecture theatre would switch off at 8 o'clock halfway through the talk. All of all the electrics, lights, everything would just power down. We've got them to stop doing this. Let's
Good
sort it out.
thinking. Good thinking. Okay, so I'm getting things here about
Yes, I'll admit people when we get closer to past.
Yeah.
Just a couple of minutes before we start.
Yeah, that's fine.
And then I'm just going to run it from the front row. Just take my iPad over there.
Okay. So by the time I've added in something on the requests you made, it's probably nearer the hour. But if you
Fine,
start to get unhappy about it, then
okay.
send out vibes that say wind up.
No, we should be fine actually. An hour, we have got time to run over if we want. And there aren't normally that many questions that will take it over a minute.
Yes.
An hour and 10 is fine.
Yeah.
That will be done. That one time. Pretty much, yeah. A bit ahead, if anything.
It's slightly ahead, yeah. Yeah. So do you think people will want to talk about things afterwards? Or
Some people might stick around, I think. I don't know how many or who, but
you can't tell?
some people will come up
Yeah.
after questions and everything while they're packing up and ask
That's fine, that's
us
good.
things. And then we do need to be out of here eventually, so we will migrate outside.
Yeah.
If people stick around. No, I think I have to head off, not that sharpishly, but
Yeah, no, it's just to know
yeah.
the process. Nothing more.
Yeah, I mean, occasionally we used to go to the pub, but that ended up being essentially just the committee going, and occasionally some of the committee's friends.
Yeah,
And yeah, we're all quite busy at the moment, so we haven't done any of them this term. We had a couple last term,
yeah.
but yeah, there should be plenty of questions, I think.
Yeah, we'll see. It's always a bit of a gamble. Actually, let me see.
So
It says it reduces the down for general life, but you need to know it. Yeah, but it wants to be general as well. Not really down. It does not reduce the general. The concept of general.
it's in some
You should have really say something. Get in fact that you get my phone on this week. Yeah. Thank you for what you do. Really appreciate it. You do that. I volunteered.
Very like the green guilds.
I volunteered to help steward the ballet recitals, which is fine. Just forgot. I'm on the front desk. Great, I'm running. Either way, I'm told my dad and the chat how to find it. I just don't know. That's what it means. I think it's terrible.
Even
I guess. Good, very good. We went to the old bicycle shop. Okay, that's very quick. We were done by like 25 to 7. 27. Oh, that's lovely. So what did you do? Oh, just a little bit longer. The hard time. They do student discounts. So maybe let's so we got 10%. Oh, that's good. Then they added 5. Chemical science next door, and they left quite loud. Yeah, I know. Once you've got people in, I'm sure it's very safe.
I have 2 people who canceled for dinner after I finished, and then right after I got an email from someone asking 2 of their friends to come. So, okay, that was helpful.
Yeah, that works. So we've still got, is it 48?
47.
47, okay.
Can we maybe release and share the now 2 more spaces if anyone wants it?
Well,
With the meals there.
no, because I think they paid already. I said yes to them.
Oh, wait.
I got replacements already.
Oh, you've got replacements.
Yeah.
And then we need to sort out the seating plan by tomorrow, right?
Yeah, I'll do it tomorrow. Okay.
But if you send me, is it still the E-shape?
Yeah, I haven't done it. Okay. I think so, because that's what fits best in the
Yeah. There are quite a few of our friends who signed up as well.
Yeah.
So we could get like 2 of the prongs of the E. That's all. Have some people on one end, and then Chris on the other end. Have me like me, Jess, and Charlie, Rich. The committee's going. And then some of them are just friends, or we've got committees, the people on the committee whose friends are coming in,
Yeah.
committee and friends on each side.
Okay, that's on both sides of the line.
Yeah, on two, yeah, and then on two, probably two tables, so quite a lot of us. I think it's really one-sided.
Yeah.
And he looked at me, he went, you've got really nice food.
It's not fair concept.
So, you know, I take it to see. I did not think it was five, it's not 5 and 4.
He always like completely forgot, so.
So what time is it?
Have we checked the?
It could not have gone worse. I want to be arts, and yet there was
We normally get a wave about now.
I do not like the. The thing is, it's just very, like we try to have that, like, when we look at math, last year, I'm really increasing.
A last roundup, sitting a little strange accident.
Whatever.
I just want to switch the board on, I help. Is it HTML or is it?
Yeah, no, it's been up once.
Can you try plugging it in again?
We pull it out your end.
Should be,
We came up the first time.
yeah. This is really weird. It should be moved in there.
Unplug yours and put it back in.
Okay. There we go. Yeah.
Hang on. Oh, this is not that technology, isn't it?
Well, I can try and restart the system just on here. We'll switch the lights off, but switch it back on. Oops. You've got USB-C that we could try.
No.
Okay.
No, HDMI.
That's really strange though.
Yeah, well, they say it was working earlier.
It's working perfectly fine.
And what did we do? We just blanked the screen.
Yeah, I literally just held to blank and then unlocked it. I can restart the system.
No, you still have several times. Yeah. And they can be a bit picky about the way out their end.
There might be slightly- Well, the only thing I can think to try is to restart. Oh,
And if that doesn't work, we'll reboot this one.
yeah, we could try next door actually, maybe, if that's unlocked.
Strange because it was working. So
It was, yeah, I don't. And next door won't be set up properly either, yeah. Because we did try to use the other one. So, right, blind HDMI. Try using. Yes.
So
Someone else's laptop, we could try and use.
well, I do have it on a memory stick, so
Yeah, we could try that. If this doesn't work.
if it doesn't come up, then I'll pull out of this and then go back in
Yeah.
and see if that. No input detected.
Really should. This happens with it. Idea.
Yeah, if you try with another laptop,
Price on the laptop.
you see if it's an issue with the system or with the laptop.
Yeah.
As long as it's got
Just do you want to do
a USB inputs.
It's got USB-C.
Sorry, as long as it's got something I can connect to.
Yes. Is it USB-A?
Yeah.
Yeah, I can see it. which end it on. Right, unplug this and then try and plug the HDMI in here. Down. Yeah. It was in properly.
Yeah, no, you're right, that they're a bit picky.
It's also what you can use the next.
All right,
So
um,
does work on guesses.
okay, let's change.
Probably one the next time.
Pardon? Should we try?
Probably one the next time, not the end of the laptop.
Okay.
Try.
That's USB, that's fine.
What was that?
I plugged it in with HDMI.
Maybe the laptop isn't set to
It,
double.
it came up at the beginning.
It was working just a few minutes
Yeah, it was
ago.
working.
Just use the, just
Okay. USB, no, HDMI. That's really strange.
Very strange.
information on there.
But do you want to come and do your own laptop things? Do you want to come and do it? So
You know where files.
You've got to set up on Zoom and all that.
yeah. Not just this one, see one.
No, everyone.
It's over the floor. Trying to be both English. Pardon?
Yeah. Maybe two, so take the second version. Yeah.
Zoom.
Have cable.
Talking program. You know, quick hosting closes for me.
Well, I'm going to stop share.
Okay. The Zoom's still working, so the camera's still working on here. So we can still run the audio from your laptop. And then I can. Should be. I hope it's on. I should be able to do
I think it's my chance. You can't find a chance of it going.
Jess, can you make me a co-host?
What?
Can you make me a co-host, please?
You want me? You?
Me.
Oh, you need to say.
Unless you want to come and log in with your personal account.
You could have done anyway. It doesn't matter.
Okay.
Like, it was already logged in. So you just search.
Should be fine. The audio is long.
Set file to the full screen. No. Go up to the top and you should be able to
Can you check the audio as well?
Yeah.
slideshow.
Oh, sure.
And then it should start from the beginning. It's posh, it's got the presenter load.
Is that right?
Yeah, I just.
By the way, it's not compulsory on Zoom.
Right. And
don't think it is going through well.
You just share the desktop, not the. That's full screen now. Yeah, it's full screen now, so it's coming up on here.
Okay.
You shared the desktop, not the,
Right, okay.
not the PowerPoint.
So it's all working now.
It would appear to be. There's nothing
Okay.
on here though.
Yeah, I blanked it, so I should be able to, unless it's in what we did last time. Okay, right, ready? Okay, right. Hi everyone, thanks for waiting. This week we've got Professor Yvonne Elsworth from the University of Birmingham. She's Professor of Astroseismology. She's also a recipient of multiple medals, Fellow of the Royal Society, Fellow of the Royal Society of Astronomical, Royal Astronomical Society, Institute of Physics as well. So take it away.
Thank you, thank you. Anything but the technology here. Okay, so I'm going to talk to you about essentially how we determine what's going on inside the sun, and also stars like the sun and similar stars will become. So it's a method very close to doing physics. All right, it's pretty good. There was a suggestion earlier from one of the people who entertained me for meals to just put our seismometer down. This is the nearest I can get to putting my seismometer down. All right, now then we find enter. Okay, so thank you for inviting me. I'll tell you about the basic ideas of the seismology and some of the early successes, because when the idea was first proposed, not by me, I was a new appointment in the field when it was just beginning. It was sort of, people didn't believe it. You know, we were talking about measuring velocities, radial velocities to and from us. And at the time, the accepted value was, well, if you could get a kilometer per second, you were doing quite well. And we were saying, nah, we can get a meter per second. Where's the problem? Okay, so people took a little convincing to, you know, why it worked and how it worked and how much you could believe the answers. I'll discuss some recent work on the sun and the red giants. Red giants being evolved low mass stars. Very briefly, I'll touch on exoplanets, finding planets around other stars, partly because it's neat, but partly because it's the source of a lot of our funding. We piggyback. And when I was invited here, two very disparate papers were quoted at me of interest. One was on what a type of star called a red clump star and Gaia that's been out measuring parallaxes, and also the new instrumentation that we at Birmingham implement. So those are wildly different topics. It's a decent measure of how interesting the area I'm in is, that both those papers I'm a co-author on, not the lead author on either of them at this point, but nevertheless. Oops, find the right button. Okay, so very basic, what's the sun? It's got several key layers. It's got a core that's the source of all the energy generation. Beyond that, it's got a radiative zone that's really quite quiet, and a convection zone that's anything but quiet outside that. And then you can talk about the photosphere, which strictly is a precise point within the sun's radius, although it's talked of as if it's a layer. Its optical depth unity at 500 nanometers precisely. And above that are the regions that people know much more about if you just would talk to, you know, a random person, the active regions on the surface of the sun, chromosphere, corona. So the outer regions I'll just mention in passing because they're of interest. It's not really what we do, what we're interested in, but clearly the corona is the visible bit that you see at eclipses. Very strange, because the expectation is you go from the core of the sun, which is really, really hot, You work your way out, cooler, 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 cooler. Ah, the corona is very hot. The corona is up to 1 million Kelvin, not quite as hot as the center, but nevertheless pretty hot. And you then get into, to understand that, you get into concepts of what you mean by temperature. You get used to the idea that if you touch something that's warm, it's hot, you get a burn. That's not what we're talking about. We're talking about the kinetic energy that is in a particle. So if one of the particles, and we're bathed in the outer corona out here now, if one of those particles, except probably couldn't get through the building, if one of them were to hit us, it would have a punch. But it's so rare, it never happens, or just expects it to happen. Material gets thrown off the sun, and understanding that is a topic in itself. These are known as coronal mass ejections. They are huge. They can interact, depending on their magnetism, with the magnetic field of the Earth, and that gets you into aurorae. And the whole topic of space weather, which again is another topic that allows helioseismology to be funded, because space weather is clearly very, very important. And to try and understand it, you actually want to see just below the surface. And seismology allows you to do that. Okay, so back to the appearance of the solar surface. A very old picture. So the photosphere, we're looking at it in visible radiation. You all know, although I always have to say it, don't look at it. It's not a perfectly bland surface. Now that at sometimes would have got me locked up for saying that, but it isn't. You can't look at it, but if you have fog, or even some weather like today with thin cloud, you can actually see the surface. You can see that you've got a disk. And the Chinese viewed the surface of the sun through mist and cloud in order to report on auspiciousness. What did the surface look like? There are early records of the spots in the sun. We have Galileo, and I'm sure most of you know the stories of Galileo. This picture actually the drawing predates Galileo. Thomas Harriot, I believe English. So in the early 1600s, with the development of telescopes, people began to be able to look at the surface or to project the surface onto something, so they then could draw what they saw, which was the only way that you could actually record something. If you look him up, there's some really quite interesting historical information about him. So they were interested in the fact the spots were there, the fact that the spots were not the same every day, and the fact that the spots moved, or at least, to be more precise, their position on the sun moved. And we know a lot more about what sunspots are. This is the picture on the left is actually quite a rare situation on the sun where there is just one big sunspot. You can see blown up on the other side, you can see it's got a very dark center, it's got the penumbra around it, and then it's got granulation, it's got sort of structure around it. To give you some idea of the scale, the Earth is up in the top right-hand corner, drawn to scale, right? So these things are big. And most of the time, what I'm interested in is the granules. It's not the sunspot, and it's not the penumbra. It looks black in the center. It isn't black. It's just cooler than the material around it. And so you take a photograph and you get your nice dynamic range, and it looks black. But it's not. It's still very hot and still quite bright. When these were first seen, you obviously have a discussion as to what on earth they are. And magnetism, I guess, was known, but really not fully understood. So one of the Herschels, I think it's William Herschel, suggested that these were caves. And it's obviously cool inside if you look at it. You draw your inferences. So if we get fed up of living here and want it to be a bit warmer, he kind of felt you could go and live in the sun. Not a good idea. Not a good idea. Okay, so sunspots are important because they allow us, and they allowed people of this time, the early 1600s, to see that, or to draw the inference that the sun rotated. And it takes about 26 days to make one complete turn. And the picture on the right is the wonderfully named Christopher Scheiner, studying the sun, who was a Jesuit. And he published not only that the sun rotated, but that if you looked at the equator and then looked at various points up, that you didn't get the same rotation period. So you get variation with latitude, differential rotation. This is not a solid body. Okay, if you've got solid body rotation, the whole lot goes together. If you've got something that's behaving more like a liquid, but clearly it's not a liquid, then you can have differences across the surface. China reported what he saw, he published it. The response of his supervisor, his superiors, was to go and get some better glasses. It can't possibly be true that this is what you're measuring. So that's the surface. What about the interior? We move to someone who I'm sure anyone in Cambridge must have heard of. And Eddington was a very eminent, very famous astronomer. And as far as he was concerned, he's writing this at the time that cosmology is really beginning to take off. At first sight, it would seem that the deep interior of the sun and stars is less accessible to scientific investigation than any other region in the universe. Our telescopes may probe farther and farther into the depths of space, but how can we ever obtain certain knowledge of what is hidden beneath the substantial barriers, the photosphere, where all the visible light gets absorbed and emitted? Now, Eddington had an answer. Eddington's answer was theory. So you took your observations of the surface, and from those, you inferred what was going on inside. Interesting point, if you look at other pictures of him, he wears glasses. He obviously didn't fancy his picture taken here with his glasses on. This is like a medieval portrait, with the tools of your trade, except he should have a pen, not his observer. So we then move on to the 60s, and a man called Leighton, again some new technology, measured the intensity and velocity on images of patches of the sun. So he looked at a little patch on the sun and could measure how the intensity varied and how the velocity of the gas moving towards you and away from you varied. He worked at Mount Wolfson, which is just above Los Angeles. We actually observe from Mount Wolfson too. It's a really nice observing site. And the smog of Los Angeles usually sits below you. It's quite reasonable, you get quite good weather. So when you make an observation, you think, what am I going to see? And he expected to see, he and his co-workers, to see the effects of rotation, and he saw that. He expected to see the signs of granulation, these little bubbles that are turning over. And he saw something that matched that periodicity, this 5 minutes with which these bubbles turn over. But it wasn't quite as he expected. He found regular structure there in something that's supposed to be random. And now obviously there's a question as to whether through the atmosphere above Mount Wolfson, you're really observing just the sun and not turbulence in the Earth's atmosphere. So he took lots of steps to try and prove that wasn't true. And these things became known as the 5-minute oscillations. Oscillations because they showed regular structure, not just a rough period, and in 5 minutes because that was the period. And in 1970, a guy called Roger Ulrich explained it in terms of trapped standing acoustic waves inside the sun. Nobody expected this to be true. And again, you've got to remember he's on a small patch. And he worked out some mathematics to prove it, and showed that they were essentially excited by the granulation, by the noise, but also damped by it. That's what's meant by intrinsically damped. So the same phenomenon is both driving and damping. And there are some interesting points in there. He put in a little note at the end that said he was grateful to to one of his colleagues, basically, for suggesting that my unexpected result, that the oscillations are self-exciting, might be more than a numerical error. This field is full of things that didn't work out quite as you would expect, but you shouldn't rule them out. Okay, so it's been known for a long time that stars oscillate. And the fundamental period of the radial pulsations depends inversely on the square root of the mean density. So Cepheids, distance scale, you see their oscillations, and that's related to their luminosity, and therefore you can use them as standard candles. But what wasn't expected was that the sun would behave like that, because the phenomenon which allows the oscillations in Cepheids and other similar stars is very, very different. They did some calculations as to what the fundamental period should be for the sun, and it was expected, and is expected, to be just over an hour. That does not match what Ulrich saw. He was looking at 5 minutes, and there is no evidence yet that the fundamental, the base oscillation of the sun has ever been observed. But nevertheless, this triggered people to go and look. People had there was technology around, and actually some of the ideas that we used for the instruments came from the early field of dye lasers. Might sound totally crazy, but lasers are, as you know, very precise frequency, very precise wavelength. And if you pass a laser through a gas, some of the light will get absorbed and re-radiated. And that was the philosophy that's used to make the precise measurements on the sun, not with a laser, but you use atomic physics and the precision of atomic physics to give you your accuracy and your precision. So one of the phenomena they expected to see was a gravitational redshift. Now again, those of you who've done your cosmology should know what the gravitational redshift is. It leads you to black holes. Right, it still costs light energy to escape from the sun's gravitational field. That, as far as I'm concerned, is a huge signal. It's just over 600 meters per second, and I'm measuring centimeters, millimeters at a pinch, right? So that's big signal. And they saw something that they thought was from the granulation, again, like Leighton, but again showed that it had a regular structure. So a group in Birmingham worked from multiple sites, which helped you make it clear that this wasn't just the atmosphere sitting above Spain or wherever. You could sort of merge signals together. And it was suggestive that this was an oscillation of the whole sun, right? The global sun. So you have this concept that you have, particularly this convection zone, this deep 30% by radius in depth, incredibly noisy. How on earth do sound waves propagate through it? The answer is they're not that heavily damped, and they do get through it. The first really definitive measurements were taken from the South Pole, where if you choose your time, you can get continuous sun above the horizon. It's not a very good quality sun above the horizon because it's still fairly low. But a French group got 5 days worth of observing and produced a spectrum that looks like this. So vertical scale, velocity, Actually, it should be power per unit bandwidth, but never mind. The frequency in millihertz, the oscillations are centered around 3 millihertz, 30 microhertz, 5 minutes if you turn it into period. The fundamental is believed to be around an hour. So this is high overtone oscillations from, well, it's about 25 in the center of the signal. You know that this is oscillations because the power is at discrete frequencies and not in between. And if you were to measure the Q factor of it, in other words, the line widths, sorry, the frequency divided by the line width, it's about 1,000 or so, I think. I've forgotten the precise number, but it's relatively high Q oscillations. So once someone has demonstrated things are possible, then you begin to do lots more work on it. And so people built new instruments to look at imaging the surface of the sun. There was some very clever stuff done, some one-dimensional work, and the work at Birmingham, which is essentially zero-dimensional, no imaging, also followed on. So let me put this into the context of music. Just to justify my title, the sun resonates like a musical instrument. So the motion in the volume of the sun due to sound, i.e. pressure waves, thought to be driven by the outer layers, the convection zone, granulation, causes minute movements of the surface and measured by either a Doppler velocity, which is what we do from the ground, or an intensity change in micromagnitudes. And it requires very high precision to make it work. So how do you tell a double bass from piccolo? Okay, well, range is one answer, clearly. Your image ought to have been really high. If I could sing, I would. So this is relevant to stars. Big stars have long periods, but it's not quite as simple as that. The other answer is the quality of the note varies. So if you think of an orchestra warming up, they all play the same note, but you can tell what instrument is playing it. And the answer is they don't produce a pure note, they produce overtones. And this, you'll see the where I got this picture from. It's a South African schools network that puts these things out. It's got some really good animations. So the waveform of the clarinet has third, fifth, and seventh harmonic, and a little bit of even harmonic. The trumpet has the first and the third, and then small amounts of the others. And that sounds totally different. It's much purer note out of the trumpet. And so it is with stars. And if anyone here is really good musician, you can tell me I've got it wrong. Basically, stars oscillate very high harmonics, very high range of harmonics, not just a small handful like I'm talking about here. Once you can do two-dimensional, you've got thousands and thousands of possible oscillations on the sun, which is very powerful. So we can go back to Eddington and say, well, he was partially right, because theory now enables you to work out how on earth your model can produce these frequencies. And some of the early successes were the sun is not metal poor, right? Or the measurements of the surface composition of the sun are the basis on which all other metallicity is equated back to 0.0. And if we'd got that wrong, there's a bit of rethinking to do. But no, the sun is not metal poor. It gave you the first time the depth of the convection zone. I said that it's 30% by radius. We know that because of helioseismology. We can measure a rotation profile of the interior of the sun. That's relevant to general relativity and the precession of the perihelion of Mercury, which is put down to, quite correctly, to general relativity But if the surface of the sun, sorry, this deep interior of the sun was fast, really, really fast rotating, that makes a difference. And you'd have to rethink some of the Einstein calculations. And we can use inversion techniques that were invented for geophysics. We can use inversion techniques to infer the sound speed profile inside the sun. We can't dig it up to see how good we are, which Earth scientists are able to do. And what was found was that the models were very, very, very close to what we observed. But the precision was another few varies better than that. And so we don't actually have a perfect match these days between what the helioseismology says about the sun and what the models say about the sun. There are still question marks. And it does produce the problem, although I think Earth Sciences has solutions to the faint early sun, to stage on the Earth where there were sedimentary rocks. The sun was only about 70% of its current luminosity, and therefore it should have been frozen. So it shouldn't have had sedimentary rocks. The answer is, I believe, in terms of what the atmosphere at the time was and the whole temperature of the Earth's atmosphere. Okay, I need a little bit of notation. It's all lifted from quantum mechanics, so you know it all. N, the number of nodes radially, the degree L, and the azimuth M to do with the longitude. And there's a model, an illustration of what one of the modes might be, color-coded for Doppler shift. It's a slightly random choice, but what's obvious from that is there are some zones in the sun where are colored, are red and blue, and there are other zones that are not. So this mode is not sensitive to the complete sun. And in particular, it's not sensitive to the deep interior. So this is n equals 14, L equals 20, m equals 1. So you can map the interior just like a CT scan works, because different modes are sensitive to different parts of the volume. And when you put all the frequencies together, then you can begin to get a 3D map. The sound speed is highest in the center because the temperature and the density are very high there. And we've got, this is very classical sound. Only the very low degrees, such as Birmingham measures, probe the very core. So you need us if you want to know what's going on in the center. The very high degree modes are brilliant at probing the surface because they just skim the surface. And like your quantum mechanics, L and M are linked. And so you have a lot of modes for a given L value, lots of M values, as long as L is nice and high. So as you can get a lot of information about the surface. So I don't know how we're going to do on time, having started late, but anyway, you can tell me not to go. Right, so a few choices. Solar activity cycle, solar rotation, and probing the nuclear burning at the hearts of stars. And I've got two particular examples there. One is the solar neutrino problem, which is a particle physics problem, and the other is the onset of helium burning in red giants, which is a problem for evolutionary studies. So not a constant star. Or I should say, page down. Oops. PowerPoint produced that nice division there. I have no idea how it managed to divide the two up like that. Okay, so the number of spots on the surface varies with time. Well, this data here starts in about 1600, which is what we were seeing at the beginning for China, Galileo, Harriot. And we're lucky they started then, because we now know there's a gap. There's a Maunder minimum. If we hadn't had the early observations, we might have thought that the sun just started showing this cyclic behavior in about 1720. But we know that there was this quiet period. And there's a lot of anecdotal evidence that links that to weather. And you've got to be very careful here because people who are climate change deniers will really hook into that and say, well, if the sun goes quiet, we'll be fine. As you all know, it's more complicated than that, but be careful. So the number of spots on the solar surface varies with time. And above the spots sit magnetic fields, or in the spots sit magnetic fields, and above the spots sit high energy electrons, protons, which are sensitive to the magnetic field. And we mentioned at the beginning space weather. And there's gorgeous pictures. Okay, so that's looking at sort of the variation of the sunspots with time. I wanted to talk a little bit about what we observed from Birmingham. We measure the sun as a star with no direct imaging. We have a bit of imaging, but by accident almost. Very high resolution method, depends on atomic physics and the stability of atomic physics. If you give me enough time, like 10 years, I can get my noise levels down to about 1 millimeter per second in the speed of light, part in 10 to the 11, which is not bad. And what we do is we compare potassium atoms in the sun's atmosphere with those in a tiny little vapor cell, 15 mil on a side in the heart of our instrument, which we put into a magnetic field, a longitudinal magnetic field. So that's our spectrometer. George Isaac of Birmingham was the person who came up with this idea, and he was working originally on dye lasers, and actually working in Australia for, I think it was ICI, so real industry origins too. And he wanted to detect exoplanets. So, as we've said before, you set up a new method, you test it on something you think you understand. So what do we understand? Well, we understand that our solar system has some very big planets in it, like Jupiter, which pulls on the sun and causes a slight wobble in the position, the velocity. And so if you set out to measure the velocity of these oscillations, the frequency of these oscillations, you should see the effect of Jupiter, right? And you do. We have to have quite precise ephemerides to actually take out the effect. The moon's also very important. And as we've seen, they discovered that actually they found oscillations of the sun. But there's a problem with the sun, if you view it in this way, that it sets. It rises, it sets. And if you're trying to measure something which is a variation over a very long period, it's no point in having 2 or 3 hours here and there and 2 or 3 hours somewhere else. You want it to be continuous. And if you want it to be continuous, you have to have a network. So you, like the old British Empire, the sun doesn't set on us. So where are we located? That's our network. 6 sites. Sort of plus or minus 30 degrees. It's sort of by chance that we've more southern hemisphere than northern hemisphere. So if you look at Las Campanas, which is stunning site in Chile, we're at an observatory there. We have our own little dome. Now you can't tell from looking at those, but I don't know what width. The dome is less, it's 12 foot across. Okay, so if I took 4 big strides, that's the size of our dome, built for the American amateur market. And we put our instruments inside. Our telescope has an aperture of about that, right? So it's not, again, not like you think most telescopes are. So South Africa, it's another similar system at an observatory. Las Campanas one in Australia, Western Australia, it's a satellite tracking station. Actually, I think it's now moribund. It's almost an observatory. Sorry, it's almost what's the word I want? A museum piece. The big dishes, the big horns. But I think they're actually going to reinvigorate it. And we're in Narrabri in the east, which is more famous for radio astronomy. The weather's not quite as good there, but radio astronomy doesn't, well, the kind of stuff they do doesn't care. And then in the northern hemisphere, we're actually using coelostats, things that mirrors that reflect in rather than domes. Mount Wolfson, we saw some of the very early work done there. We're up a tower that's 60 foot tall. So they started by building long, thin, on the ground, horizontal equipment. And then they realized if they turned the whole thing up like that they got above some of the disturbance that's there on the ground. So it's the same thing as an instrument lying all the way down with a nice big magnification, but it's turned the other way up. And Izania in Tenerife, and I'll show you some more pictures of Tenerife in a minute. We are actually trialing some new technology. And that's one of the things that I was asked to say something about. Things have moved on since the mid-90s when we built this. And in particular, go-to telescopes. So the amateur market again. So we are now moving towards using open source versions so that we can make it do what we want it to do, not less geared to just observing 1 or 2 stars. But again, it's some very pretty instrumentation. The ground rules are you can have a failure once, but not twice. All right, so we try and put in the kind of condition monitoring that tells us that our hard disks are about to fail or our motors aren't really doing very well, whatever you like to think. Is it going to rain? So you don't just detect rain, you detect cloud. And that's really tricky, actually. In daytime, it's easier enough in the night, but in daytime, it's really tricky. So there's a lot of very nice electronics in here, and it has to be done on a shoestring, because if you get funded, as we have been since the early 90s at a reasonable level, every time the committees want us to do it cheaper. So can I drink some of this water?
Yeah.
So we run on absolute shoestring, but it's very, very nice, simple, straightforward commercial instrumentation turned to our interests. Okay, this is Tenerife, Izania. I don't know whether you know it at all as a holiday resort. In the back there is KAB itself. And it's not on here, you'll see it in a minute, it's the television tower. Okay, you may remember that last summer it was very hot, very dry, and there were fires. So this is the, let's see if this will work of this. Oh, that one is not going to. That is one of the problems of having it running off the USB stick. It's not going to do it. I'll show it to you after it's on my machine. Essentially, the fire burnt all the way up to the tower, the German tower, but did not quite burn the German tower. Very frightening. The thing in the background is the television mast, broadcast mast. And one of the problems here is that at observatories, you want to stop the warm air rising. You want to stop currents of air. So what you do is you plant low bushes, low, dry. The fire really quite likes it. So it's pretty dodgy. I don't know how they're going to cope with it this summer, actually. I don't know what they're going to do. Okay, so there's our sunspot data again. What we were able to show in Birmingham is that the frequencies of the oscillations changed with the activity of the sun. So we're going to look at an average frequency shift versus Julian date from about 1975 to 88. And the observations show that the frequency is higher at higher activity. So there's our Nature paper. So the data are the error bars. The dotted line through it is a solar activity measure. We waited very patiently at sort of this point, make sure that the signal turned and wasn't just drifting one way, because the activity was changing, so ours had to. You might look at that and say, that's rubbish data. It was more than a 3 sigma effect. And the point I would make perhaps to the students sitting here is when you have discoveries, if it was like stuck out like a sore thumb, lots of people would have it. So there's my modern data. Okay, you wouldn't argue with that one. But that wouldn't have got us Nature, because someone else would have got there before us. So it's very clear that the frequencies are changing with activity. Cause and effect or chance? There's a chance, right? Again, a letter in Nature, which is a graph of the number of pairs of breeding storks and birth rate. And it shows quite a nice correlation. Right? You might be tempted to say, don't believe that. But not all correlations are real. But it was shown by Mike Thompson that actually we can put some very good physics behind the fact that the frequencies should change with the magnetic field change and very close to the surface. Okay, so the current sun, we're very close to maximum. For once, for this cycle, cycle 25, the oscillations are actually slightly stronger than the predictions. In the last couple of cycles, they've been lower than the predictions. It may be that the activity measure is starting to climb up again. If you look at the graph along the bottom, you'll see that not only is there the 11-year periodicity here, but there's longer term periodicities in here as well. Not understood. No one seems to be able to reproduce them. But we're probably close to maximum. And we were having a discussion about, or I was listening to one on going to look at the Northern Lights. I'm not sure more that CMEs are strongest at maximum. But, okay, so this is Birmingham data, and at this time, the only thing I get you to take from it is there are different frequency bands. Strong signal in the top one, less strong, very little as you go down. The data here are probably the mode has an outer turning point, which is probably below where the magnetic effects are happening. What I am interested in is the fact that this cycle here, which was nice and strong, does show an effect there. Whereas here, it's much harder to see it. And I don't think it just scales. I don't think it's just that the sun's activity is going down, because the second peak was actually reasonably high. And we think there's actually been some changes in the outer layers of the sun from this. Okay, so rotation. That's a picture of the sun in Doppler shift from 2-dimensional measurements that allow you to image the surface of the sun coming towards you with the blue shift, going away from you with the red shift. The sun rotates with about 2 kilometers per second. You can see the scale along the bottom. So if you want to see any big structures, you actually have to remove that. Okay, so I said earlier that China was able to show that there is differential rotation. The rotation rate is not the same at all latitudes. If you think of your very basic, simple physics, if you think about a liquid or something, a plasma, and you're rotating it, you would expect that on cylinders, in other words, distance from the rotation axis, the rotation rate would be the same. You'd think that that's what would sort of determine the effects. That was the prediction. That was wrong. You can see that this is the picture over here. This is very much not on cylinders. It's much more radial. What the calculation left out was the Coriolis effect. You get to a certain point when you're going in that the variation with latitude stops. The sun starts to be much more solid body. For that, you need BiSON type data, our type data from Birmingham. So the thought is there's perhaps a magnetic field in the real inside base of the convection zone that just ties all the material together, but outside that in the convection zone, you get the rotation. You'll also notice that we can't image the poles because we can't see them well enough, because these are radial oscillations and we're looking almost sideways on. Okay. So is the rotation rate of any one latitude constant? No, it's not. It varies with time. And these are slightly difficult to get your head around, but there are migrating bands of faster and slower average rotation, which follow the magnetic cycle and are predictors of the magnetic cycle. So this is measured with the two-dimensional stuff done from a ground-based network of GON and some satellite data. So I'll show you what the sunspot positions look like. So this is known as the butterfly diagram, because it looks like a butterfly's wings. Many years across the bottom here, sunspots start at about plus minus 30, 40 degrees north-south, migrate towards the equator, and then actually you can't see it, but there's a reversal. This is just numbers here. There's a reversal of polarity, and you get the same behavior again. Starts at high latitude, works its way in. So there's an 11-year cycle if you just count numbers, 22-year if you take account of the polarity. So this is a plot. So essentially time along the bottom and latitude vertically. If you see red, then you're seeing faster than average rotation for that latitude. If you see blue, it's slower. And you can see that there's very clear migration towards the equator. So there's cycle 23, cycle 24, cycle 25, that's the one that's coming to a peak now. Now look at the higher latitudes. There's a nice black band up there. Where's the next one? Okay, I would have expected to see another nice black band being the start of cycle 25. It's not there. You can look at these slightly differently, but instead of sort of averaging over 2 cycles, look at over each cycle separately. It shows the same effect. And what we think we're seeing here, if we plot how cycle 24 compares with cycle 23 at a given latitude compared to the average, that as nearer the equator, these low here, then the cycle 24 was a bit faster. When you go to higher latitudes, it's definitely slower, and you can see the error bars. This is quite a large effect. And what it's thought to be due to is a very weak polar field, so that not only is there this cyclic behavior, but it's not even repeatable. Okay, I'm probably going to skip that anyway. I can tell people about it afterwards. It's it pleases me because astronomy said particle physics was wrong. Particle physics was wrong. Okay, other stars oscillate, and that's what's known as asteroseismology. and I'm just going to talk about low mass stars. We've seen that the fundamental period scales with size. You want to look at an enormous number of stars, whereas from the ground with the stuff that Birmingham does, we look at one star, we look at the sun. That won't hack it if you want to look at the Milky Way and to measure what's going on. So you just about have to have an image onto a CCD, and then you have to look for small fluctuations in intensity, micromagnitudes. Very, very difficult to do that from the ground. Tranquility of space makes it possible. But there was no money, kind of important. But if you want to find planets, it turns out, around other stars, it turns out that the kind of sampling time that you need and the kind of noise level you need does astroseismology very nicely. What is more, if we can find that a star is oscillating and you find a planet around it, we can tell you about what the star is, because the early planet finding is done by the transit method. The planet goes across, intensity drops. That gives you relative areas, planet to star. But astroseismology can give you the absolute size of the star. So consortium, which we were part of, led by a Danish group, persuaded NASA that as long as we promised on pain of death not to find any planets, or at least to tell them if we did, we were allowed the data in the proprietary period. And suddenly you can measure thousands of stars with their amplitude fluctuations. Anyone here is an amateur, knows where Cygnus is. One or two people might. Many people who don't, who use the data don't know where Cygnus is. Okay, so this is an early success. You can see February 2012, a rocky planet, 1.5 times the size of the Earth, orbiting every 2.8 days, not exactly Earth-like. At this 4.3% of the Earth-Sun distance. I think Mercury is, what, 20% of the Earth-Sun distance? So this is awful close. But we could get astroseismology from it, which told people absolutely what the star was there, which was what they were supposed to do. That's clearly an artist's impression. Okay, so that was a star sort of like our sun, a main sequence star. An unexpected bonus of Kepler mission, a mistake, was red giants. They essentially didn't do their selection criteria correctly because they looked for cool stars, but they forgot or didn't properly handle the fact they could be a big cool star or a small cool star. So there were an awful lot of red giants measured. And before the observations were taken, there was a lot of discussion as to whether you would see any more than simple radial oscillations. Could you see the ones that are L equals 1, a sort of dipole, quadrupole, whatever? And you could, and you get amazing pictures. They have rotation rates in the center that are very high, which is what you sort of expect from collapse, right? I've got a couple of pages on the collapse, but the center will collapse as the star goes into being a red giant. That means the outer layers expand. The luminosity depends on the surface area, so these guys are bright. And the collapse and some element of conservation of angular momentum requires the center to spin up. And we see that, but not as fast as expected. And these are brilliant for galactic archaeology. In other words, can we understand our Milky Way? Because they're bright, and therefore you see them far away. And because the length of time it takes to go from being just past the end of the main sequence through to just the beginning of a phase, but 2 is actually quite a short time. You know their ages. So if you really want to understand the structure of the Milky Way, red giants are there. But key to this is where is the onset of helium burning. Okay, so energy generation, burn hydrogen. When you run out of hydrogen in the core, then you start to burn hydrogen in shells, and you've got an inert helium core in the center. Outer regions expand, inner regions collapse and get hotter, and you get to being a giant. And if I was to show you some of these stars, and the person who did this for me didn't make the tracks follow the masses correctly, so I apologize for that. But you basically have main sequence, evolution like that. It goes up way, way, way up there to the onset of helium burning, and then it comes down and settles into a phase which is helium burning, a sort of helium main sequence. Disentangling this lot, are they going up? Have they come down? You can't tell from this. You really can't tell. If I was to put in a wider range of masses and metallicity, you'd be stumped, absolutely stumped. Oh, the battery's running out. And what was about to disappear. Okay. Okay. So we turn to seismology for this, and you introduce a new set of modes where gravity is the restoring force. Yeah. Remember this. I'll just try to bring you to that one.
Oh, it's the USB-C, okay.
Okay. Okay, so if gravity is the restoring force. Well, I thought so. If you think about the difference between granulation, which is convection turning over, and small oscillations driven by buoyancy, a packet of gas has to make a decision, or the conditions make a decision. It's either one thing or the other. And so propagation through the convection zone for these modes is impossible, which is why we don't see them in the sun. They're strongest in the center, and a great probe of those conditions. But you can get coupled oscillations if you happen to match the frequency of the pressure modes with the frequency of these gravity modes. And you have an evanescent zone between that's not too big. You can actually couple the two sets of oscillations together, and you get what are called mixed modes. So this, you can form your judgment here. That's one sort of star, that's another sort of star. I think I could get you to have a show of hands, but roughly the same frequency range. We're now in microhertz because these are big stars. These lines here are the basic period repeats of the different orders. This is a much simpler spectrum than that one that's got an awful lot of grass in it. And what we find here is this isn't grass. This is the so-called mixed modes. And here, although there are mixed modes, they are so close in that you can't really see them. And if you, again, how you choose to plot your data is important. If you plot the separation of those orangey bars I showed against the period spacing of those extra bits of grass, then we suddenly find there's a region up here and there's a region down there. And those two classifications, stars going up the red giant branch and stars that have already become red clump stars. And if I now show you an HR diagram with color-coded for what astroseismology can tell you, there's the stars going up These are the low mass stars that have started to burn helium. These are somewhat higher mass stars that have started to burn helium. Now, I probably can't properly discuss one of the questions you asked me, but you'll notice here, these stars exist in a really narrow band. And they have, because of the conditions in which the helium burning starts, there's a well-defined mass of helium there, and that's the source of the energy, and therefore these are standard candles. So just like the Cepheids, and they have proved to be very important in determining offsets, for instance, in Gaia. And in recent years, my role has been to ID those. I have a very neat way of doing it. Okay, so this is the bit that I'm not talking about because I haven't got the time, but it's essentially took models and Gaia and took the astroseismology data for the red clump and essentially looked for systematic errors in both of them because they're measuring the same, well, you choose the same cohort of stars. Okay, so lots and lots and lots of diverse applications. Physics of the solar interior, solar and stellar activity cycles, stellar evolution, galactic archaeology, host stars of planets, solving particle physics problems, space weather. And the takeaway message here really is theory and observation have always gone hand in hand. An advance in theory means you can test what an advance in observations give you. And that's it. Thank you.
We've got a couple of minutes for questions if there are.
Otherwise, I'm happy to talk outside if we really ought to leave. Go on.
So are these oscillations really, are they purely radial or are they also transversal? Or do we count the transversal ones?
The pressure modes are essentially radial. The gravity ones are not. So both.
Thank you.
We can tell that they're radial at the surface because of the way if you go from the equator when they're coming towards you like that, and then you go up to the top and they're going that way, you can see the fall off. So you can tell they're radial. But they're obviously high order. Go on.
You said you could measure the size of the Kepler 21 star, but you didn't say how big it was in the measurements. How big was it?
It's a little bit more evolved than our sun, so a little bit bigger than our sun, and a little bit more massive. But I can't actually remember the 10% or whatever. But that's the sort of level. There are a whole load of them. That's just one example. But when you're getting to the red giants, the red clump stars are 10 solar radii. If you head way up the red giant branch, you can get to 100 solar radii, and then you begin to get significant mass loss, and that's a whole other area to look at.
We've got one from Zoom.
Okay, there's one at the back there too.
Yeah, in just brief overview of the neutrino problem, which is okay.
Sorry, over.
The neutrino problem, particle physics.
Oh, the neutrino problem.
Yeah, just a
Yeah.
outline.
The neutrino problem was that when you made the measurement of the Earth, there were 1/3 what the solar physics said. Okay, and the feeling was that we didn't understand solar physics properly. That's good. Yeah, that we didn't understand the solar physics properly, and therefore that the temperatures are very high, the temperature gradients are high, and therefore if the solar physics have got the conditions in the center very slightly wrong, well, who would blame them? We've done our best. And so people built models and used our data, this is Birmingham data, for the modes, the radial mode that goes all the way to the center and a quadrupole mode which doesn't quite go all the way to the center. So the frequency difference between those two is relatively sensitive to the center of the sun, and the temperature of the center of the sun is what would change the neutrino rate. Okay, and you put in various models, so very standard models, mixed modes, which said the temperature gradient is not as steep as you think. There is convection there, and it's making things flatter and therefore not as peaked, and that would cut the rate. Or you put in these wonderful goodies, these weakly interacting massive particles, which would help provide missing mass in the universe, and they would settle into the gravitational field of the sun. And because they don't interact, they'll travel a long way from one point to another point before they lose their energy. And so they, what's called as thermalize, again, they reduce the temperatures. And those models, so we discovered that you could produce a linear plot, basically, and plot slope and intercept. And the WIMP models sat there, the mixed mode models sat there, and the real data sat there 10 sigma away. And not long after that, it was realized that neutrinos had a tiny, but nevertheless significant amount of mass. And the neutrinos interacted with, I think it's the mass of the sun, actually, as they came out. And therefore, they changed from one flavor to 3 flavors, and you expect 1/3. But it's like when you've lost something and you're sure it's not somewhere, not in a particular place, you don't find it when it's in that place. Yeah, when you're sure you're not looking for something, you don't see it. So that was it. Well, you had a question on. Oh, okay, good. That was convenient. Yeah.
So I found it very interesting when you said that we can use that sum of amplitudes from all the modes to image the star like a CT machine. I didn't really understand what we are reconstructing exactly.
These, at the simplest possible level, the distribution of the speed of sound inside the sun, so temperature, root T upon M, density, the temperature and the density.
Okay.
So very classical sound speed. You can be more sophisticated and therefore and test for other parameters, other combinations. But the simplest possible level, you're measuring the sound speed, the map, 3-dimensional map of the sound speed.
Any more questions? Okay, we have another round of applause. Thank you very much for coming. See you next week at 5 o'clock. We've got the annual dinner in the evening at 5 o'clock next week.